I want to welcome our eminent speakers today, Mr. Prabhu Santiago from AVL, Mr. Pratish Joshi from Dana, Mr. Yatish Muthappa from Mahindra Electric Mobility, Mr. Kundan Yadav from Bueller Motors, uh, distinguished participants from the industry, my colleagues and friends, a very warm welcome to you on this webinar on automotive electric vehicle testing and challenges. The world is now in the middle of new mobility revolution. It is now important to understand that mobility as a new paradigm from moving from ICE engine based technology to an electric vehicle based technology. I had so far been talking in many forums on emission control, and that was something which we all knew. So electric mobility has thrown new challenges, also very large number of opportunities. So e-mobility has built up an ecosystem wherein a lot of startups are getting into this area of industry, this area of domain, which was not earlier possible in the IC engine-based technology. And it's very encouraging to see that India has very young entrepreneurs who have come forward and they have taken this challenge of developing vehicles which are powered by electric mobility. It is important to understand that India has committed to reduction in greenhouse gas emissions by 35% by 2020. And in order to achieve these committed targets of COP26, the carbon intensity reduction is aimed at 45% by 2030. And for the automotive sector, the most promising technology to achieve this near-term target looks and is EV. And that's why there's a lot of focus by Government of India in promoting this industry and this sector. There are PLI schemes which have been announced for advanced chemistry manufacturing, PLI scheme for advanced automotive technology, and also FAME2 scheme. These all are the enabling environment and policy measures which government has rolled out to promote this ecosystem in India. We have seen, a drastic adoption of a very accelerated adoption of electric mobility in the country past 2-3 years. I think 5 years back, we would not have imagined that there will be such a great transition from ICE to EV, but it has taken everybody by surprise. Not only the traditional OEMs who had been manufacturing ICE-based automotive technologies, but also, connected supply chain manufacturers, the policy makers, we are not aware that they need to have special policies, special regulation standards for enabling this technology to be introduced in smooth and safer mode. We talk about a lot about efficiency in the paradigm of electric motors, and electric motor being the heart of the power generation for automobile. It is very important to understand how the efficiency of this particular power mode can be enhanced, and that's the challenge that is being faced by a lot of electric vehicle manufacturers in the country. And there are efforts being made by supply chain manufacturers in addressing these issues. We also know that it's not only the electric motor which is a challenge for enabling this technology, but it is the battery which is also the heart of the vehicle, which has thrown a lot of challenges in terms of one being very specific technology dependent, and then secondly, India doesn't have a manufacturing base for cells. So our dependence on battery manufacturing becomes again an import dependence to other countries other than India. And there is a need to find solutions so that we gain independence from the import of batteries, also for permanent magnets. So these challenges, a lot of people, the industry, academia, researchers are addressing by various means. So there are technology transfers happening. There are special PLI schemes being created so that this particular issue gets addressed. There are special focus on research and development of new chemistries. So I'm sure that any technology transition always faces some initial challenges, and initially it looks very difficult to overcome those challenges. But I think over a period of time, human mind is so innovative that we try to find out the best possible solutions, and we achieve those solutions. And it's only a matter of time that we can see that India will develop itself into a very important source of electric mobility for the world. We are going to be source of battery development in the world. So there is a concerted effort which is required by industry, academia, researchers to build that ecosystem, wherein we are self-reliant. Atmanirbharta will only come when we don't have dependence on any technology for outside India resources. And I'm sure today's topic, which is very important to the EV sector, will throw a lot of important aspects on the development of electric motors for various applications. We are seeing a lot of electric vehicles being developed for two-wheeler, three-wheelers, e-rickshaw. So these are small mobility solution and also large implementation in buses also. And I'm sure we will have, and also now the passenger cars are also there, which are EV passenger cars, uh, which were not very easily accepted by customers 3 years back. But now customers are becoming aware, and they have developed the confidence on the technology. Then now customers are depending electric mobility solution for pass car also. So I am sure today's webinar will throw a lot of important aspects on this technology, and it will bring value to all the participants who are there present. I'm told that over 418 registrations for this webinar has happened, which is a very overwhelming participation by all, and I am sure each and every one of the participants will be benefited by the presenters today, who are from going to talk about this particular aspect. Mr. Santiago from AVL, Mr. Joshi from Dana from Motor Manufacturing, Mr. Yatish Muthappa for Mahindra Electric in terms of their experiences for electric vehicle in application in passenger cars and other sectors. And a startup like Euler Motors will also throw up their challenges as to how they have overcome the challenges and what constant challenges they are facing. And I'm sure that with the active participation of all, it will become a very important and informative session today. I wish everybody a very successful webinar. I want to thank Sitaram Kashyap, my colleague, Jasdeep Singh Panesar, and the whole team of ETC who have organized this webinar under Aspire portal and on a topic which is very relevant to the industry today. Thank you so much. Have a nice session today. Thanks.
Thank you, ma'am, for the welcome and enthusiasm. I'm sorry there was a glitch in the internet connectivity. Let me start again once. A very good morning and warm welcome to all the esteemed guests, speakers, and my dear colleagues from industry. We feel privileged to extend a cordial welcome on this webinar. In this global mobility industry, the shift toward developing electric power transport has created a need for an agile approach in the research and development of EVs. India is still in the early stages of the EV revolution and overcoming challenges in transition from IC vehicles to electric vehicles in India. Electric vehicles promise zero tailpipe emissions and a reduction in air pollution. The Indian government has created momentum through its FAME schemes that encourage EV adoption and in some segments mandates the adoption of EVs with a goal of reaching 30% EV penetration by 2030. The policies implemented over the years from FAME 1 to FAME 2, FAME 2 to PLI have given the industry, OEMs, component manufacturers, and end users a phenomenal boost, and all have benefited significantly, causing the shift and acceptance of EVs in India that we see around us today. Foreseeing the electric vehicle scenario and opportunities in India, ICAT has taken various actions to support the OEM, new entrants, and component manufacturer for their development of EV motors. Today, this webinar is organized in the same context to bring the technology providers, new players, and OEM experts on one platform to demonstrate their thoughts and knowledge. ICAT has been working tirelessly to support the EV business by not only providing the regulatory services, but also by developing testing infrastructure in India and executing DVP testing on vehicle as well as on e-motor test bench validation. It makes us immensely proud to work with Indian companies like Tata and Mahindra, who have successfully accomplished their passenger and LCV segment e-motor and inverter systems in past years. The initiatives like this webinar today are being taken with an ultimate aim to support and make in India vision to make, validate, test and deliver EVs in India. Today, we will be having 4 presentations by our distinguished speakers who will enrich our minds with their experience, thoughts and knowledge. Well, without taking much of the time and to begin the day, we'll now begin the session with first speaker, Mr. Prabhu Santiago. He's from AVL, Austria. Mr. Prabhu has got masters in the field of automotive engines. He's graduated from IIT Madras. He has 18 years of experience in calibration for powertrain development and technical software solution development for battery electric vehicles. I will now request Mr. Prabhu to start with this presentation. Mr. Prabhu, you can share your screen. Hello, Mr. Prabhu, can you hear me?
Can you hear me?
Yes, we can see your screen and hear you also.
Okay. Okay, Jasdeep already gave an introduction to me, but however, I thought I will a little bit make debrief on this one. Myself, Prabhu Santiago. Currently, I'm working with AVL Graz in Austria. I work there as a Syrian Solution Development Manager. So basically, we are providing software solutions for development of in the automotive area in various domains like cybersecurity, ADAS, electric powertrain, and conventional powertrain solutions. So here today the topic is the e-drive topic, which is a very important component of electric powertrain. So let's directly jump into this topic. Okay, so let's take an electric vehicle. As you can see, in an electric vehicle, I hope the picture is clear for you. We see that the e-motor is basically the heart of the engine, and then you have the inverter control unit, which is the brain of the vehicle, where these two, which is called the e-drive, basically affect the NVH, the handling, the performance, the efficiency, and the safety. These are all parameters. These are all important attributes which is contributed by the e-drive system in a battery electric vehicle, yeah, in EV, basically. Okay, so as you can see, as far as the e-drive development is concerned, the e-drive development starts a lot in the simulation environment. As you can see, all these attributes, the starting point is the simulation environment, and after that you have the testbed environment where you do a lot of additional activities on the side of efficiency, performance, functional testing, all these activities. Okay. So if we take the testbed environments, there is a lot of tasks that is done. For example, on e-drive testbed, there is a lot of tasks like system efficiency optimization, torque ripple reduction, NVH improvement. And then, for example, on an inverter testbed, there is a lot of tasks done like safety and function testing, e-motor production tolerances analysis. Okay, so I would like to take one example today, which is the and discuss in detail the solution AVL provides to this task. Okay. Let's talk about the task first. So as you can see, you have
Hello, hello, Mr. Prabhu. We cannot hear you. Can you check your audio? Hello.
I
Yes.
believe there was a small problem, right?
Yes. Uh, we can hear you right now. You can continue from that slide.
Okay, this slide is this is the slide where we left off. Okay, so you see that there are two parameters that need to be that need to have a trade-off optimization. One is the total system of efficiency, and the other thing is the NVH reduction. Okay, so how does this system look like? It looks like this, that you have a e-motor testbed. This is your e-motor, and then you are running it using a dyno, and then you have a sensor, the accelerometer sensor in the stator housing, which is measuring the NVH parameters, and you have also a dynamic torque transducer, which is measuring the torque fluctuation. Okay, this task we have executed using our AVL system of a permanent magnet synchronous motor and a three-phase inverter. Okay, now what are the parameters that affect the system efficiency and the NVH? So considering there are four parameters that we have varied. One is the currents, inverter currents, namely the ID and IQ currents, the speed of the e-motor, and also the switching frequency. Okay, these IGBT switching frequencies. These are the important parameters that were varied to do the task. Okay, to make the best efficiency optimization versus NVH optimization. So when we do this task, there is a lot of challenges. What are the main challenges? The main challenges are during doing this task, what happens is there is during the speed variation, the rotor and stator temperatures need to be maintained. Okay, and you see that with varying speeds, what happens is that your modulation ratio limit, which is always changing. Okay, this is always changing. This is like an ellipse which changes always with respect to speed, and we need to take care of this modulation ratio limit. Okay, we need to measure at the borders the temperature increases fast. Moreover, we need to challenge the results that are coming from the simulation, and we need to find the best optimization of the ID, IQ, and the currents coming in. Okay. So from AVL side, the solution we have is the Cameo 5. What is this Cameo 5? Is a software that we have developed. Okay, this is a unified testing intelligence software. For example, this is like on a component test bed. For example, on an e-motor test bed, this software is interfacing with the automation system. Okay, it could be a Puma or any other automation system. This is interfacing into the automation system, and it is helping to do the intelligent automation for functional validation and also the AI-based optimization for system efficiency, which is NVH optimization. I will explain this better in the next slides. Okay, this is a short overview. So Cameo is able to do calibration and optimization tasks. It's able to do function and performance validation and also functional safety test. And what is interesting from the previous slide is that it is not only across the component test bed. Once you create the test cases, these can also be shifted to all the environments, because as you know, in a BEV, you start with signal level testing in the hardware and the loop environment. Then you also do some software checks in the software environment. Of course, the whole system validation you do on the vehicle test bed or on the road. So in this case, the Cameo solution can help you to take the test across all these platforms seamlessly. Okay. And finally, this is how test is parameterized in Cameo and run on a component test bed. Yeah. So here you vary the speed and also you vary the IDIQ parameters. Okay. Now we come to what is this AI-based algorithm which is acting inside Cameo to make this task easier for the customer. So what happens, as I told you, the limits, the modulation limits are changing with the speed. This means that you can give the software what are your targets. For example, you can give the target that minimize my NVH and also maximize the system efficiency. Okay, these are two inputs that you can give the software. Okay, and you can also give the software the inputs of the limits from the simulation output. So then then Cameo is running the test on the test bed and it is building some online models. So by building online models, for example, not only for the limit parameters, but also for the system efficiency and NVH. So once the models, the online models are built on the test bed, then automatically it populates the variation space, that is the parameters space where you are varying, and then puts points only in the interesting area where there is a trade-off between system efficiency and NVH. Okay, so basically Cameo is doing a machine learning of the system and trying to put the points only in the interesting areas where you have the best optimization between the system efficiency and the NVH. So once this point is made, okay, it goes in loops and then it tries to populate the whole region, okay, such that you have points measured in the most interesting area where you have the best trade-off between system efficiency and NVH. Okay, this is how measurement data will look like. Once you have this measurement data from the test bed, then you can make a mathematical model in Cameo representing all your output parameters. For example, your losses, that is your efficiency, your NVH, as a function of all the variation parameters like ID, IQ, switching frequencies. Okay, you can make a model and then you can do an optimization saying that I want the best setting across all the speeds such that I want the best compromise between the efficiency and NVH. And then This is an optimization task which we did for the setup, where we optimize for the best efficiency. For example, these are the best efficiency setting for the ID, IQ, and other parameters. This is the best settings for the best NVH, and this is the best setting for the trade-off between efficiency and NVH. Okay. Once these settings are available, you can put these settings and then generate the required maps. So ID, IQ, switching frequency maps you could generate in this software. Okay. So all these parameters of the motor control unit are calibrated in using the software Cameo. Okay. Once the maps are calibrated, offline itself you can check over different cycles. Okay, for example, we have checked it across a WLTC cycle. What will happen when we run these maps across a WLTC cycle? What will be the effect of efficiency, and what will be the effect of NVH based on this optimized map settings which we got from the model-based calibration approach of Cameo. Okay. This is some results from the test runs that we have run basically. As you can see, this was the baseline, which is usually people go with the maximum torque per ampere settings. This is let's say the baseline settings. The best optimized NVH settings would have been this, and the best total system efficiency would have been this. And the yellow one is the trade-off optimization that we got, which has the best compromise between efficiency and NVH. Okay. So these are the results. And as a final conclusion, just hold on a minute. One second. I'm showing you a web page which is called experience.avl.com, where you are able to see Cameo 5. And if you go into this web page here, Cameo is not only used for e-drive applications, but also for battery, for fuel cell optimization tasks and verification tasks. And then let's now go into the e-drive. Here you have what I talked about. Okay, and here are our references. So we have been successful across the globe to implement this methodology, and we have established papers with Hitachi, Astemo in Europe. This is one of our reference customers. We also have references from GKN, which is also a leading e-drive manufacturer. So yeah, this is a web page where you can see and even try the software, and you have all these references, and you have several articles that we have written on this, so that you can go through these articles to understand the solutions that AVL has developed in e-drive development. So with this, I would like to conclude my presentation. Thanks a lot for listening. I hope this presentation was useful to you. Thank you.
Thank you, Mr. Prabhu, for sharing such insightful thoughts and giving us overview of e-drive system. The participants can raise the questions in the inbox section, which shall be answered later by a respective speaker. We shall have the question and answer session at the end of this webinar. The next speaker is from Dana Technical Center Limited, India, Mr. Pritesh Doshi. He has done masters in mechatronics and has been working for last 18 years in automotive domain with OEMs. He has 9 granted patents and have vast experience in product development and e-powertrain system. I shall now hand over the screen to Mr. Pritesh Doshi for the presentation. Mr. Pritesh, you can share your screen now.
Yeah, just a moment. I'm just trying to share my screen. Yeah, show my screen. I got that option. Perfect. Just let me know when you can see my screen.
Yes, we can see your screen.
Okay. Okay, so first of all, I would like to give a very warm welcome to all the participants and also all the honorable guests here. I would also like to say very much thanks to the ICAT team for giving me the opportunity to represent the organization and talk on behalf of Dana here. I would also like to say thank you to all my colleagues in Dana who worked with me in preparing this presentation. So what I'm going to cover here is a slight overview about our organization Dana, and would also cover the development, testing methods, and the different stages which are involved in the development of motor and inverter. And then we would also cover why this is constantly popping up. And we'd also cover about the testing, and we'll also cover the methods which are involved in testing and different legs which are used in testing of motor inverter, and what are the different challenges that we have faced so far, and what we can do together as an industry and regulatory bodies in the India to accelerate the development and testing of motor inverter and then adoption of electrification in the country. So a little bit about Dana. So Dana is an organization which is more than 100+ years in the industry, and we operate in 3 major markets: light vehicles, off-highway, and commercial vehicles. Our business covers 3 segments. Light vehicles, we offer the drive systems. Off-highway, we offer the drive and motion systems. For commercial vehicles, we offer the drive and motion systems. Further to that, we have one of our business arm which offers the power technology, majorly the cooling systems and gaskets and sealing systems. Further, we also offer fuel cell plates and technologies for basically the fuel cells. We have our revenue majorly coming from North America, Europe, South America, and Asia Pacific. In terms of technology, we offer drive systems, then motion systems, electrodynamics, thermal systems, majorly cooling and fuel cell plates, digital solutions with different kinds of controllers and softwares for the powertrain application, and sealing systems. Okay, so we are a partner for most of our customers in the industry, and we offer the complete solution for e-propulsion capabilities from a single source. So we have battery management systems as a part of our portfolio. We have software and controllers which are used for powertrain, vehicle control unit, motor control unit, transmission control unit. We do offer different thermal management solutions, hub systems, differentials, then high performance transmissions, and we offer motors and inverters as a part of low voltage applications and high voltage applications covering different vehicle segments. And we not only offer the individual components and system, but we also go further and offer the vehicle integration services to our customers to either convert their existing fleet into electrification products or bringing the new products to the market with electrified drivetrains. We are recognized in industry with more than 25 customers have awarded us for different categories in 2021 and 2022. These are some of our customer awards for this year and last year. We have a market reach for various segments, as I mentioned. So we cover light vehicles ranging from two-wheelers, three-wheelers, four-wheelers, and commercial vehicles ranging up to trucks and heavy vehicle applications, off-highway applications, and some of the stationary applications also. In India, we as an organization are present in more than 18 plus facilities. We also have our research and development center in India, which is based out of Pune, and we support domestic business plus global business from here. We have market reach for different segments, and we do offer our electrification products like controllers, vehicle control unit, inverters, low voltage and high voltage motors. And we are one of the major supplier for electrification products in the Indian market right now. So little more going deeper into motors and inverters and what are the different kinds. So we as an organization have motors, inverters available for low voltage applications, high voltage applications, and also the motors are present in different architectures and different rotor types and rotor designs. So majorly like inner rotor, outer rotor, both kind of applications and both kind of motors are available from our portfolio. And we do offer the motors in different technologies like induction type, synchronous reluctance, synchronous IPM, and SR-IPM. So in terms of generation of torque capability, we have reduced rotor content where the magnet content is reduced, and as we go on to the right side, we have variable reluctance which has intermediate rotor magnet contents, and then when we look for the high torque density motors and high power density motors, then we have also heavy magnet content motors as a part of our portfolio available to customer. So in terms of our low voltage motor portfolio, we have application motors which are suitable for applications into two-wheelers, three-wheelers, light vehicle applications like even passenger car and light commercial vehicle applications. And these are specs. In the interest of time, I would not be reading out all the specs. These are available on our website. I'm just showing you the portfolio. We not only offer the motors, but we offer the complete system. So we offer motor plus inverter as a single-handed solution. So our controllers are very well trained with our own motors, and that can be used with other motors also. So we have controllers which are series 1, series 2, and series 3 inverters which are currently available in the market, and we are also currently working on series 4 inverter, and this inverter is compliant with industrial functional safety standards, and we are also working on making this compliant with SIM level 2 processes. And this inverter is based on OpenECU based software standards, so it gives the opportunity for OEMs that they can further add in their custom software along with our base templates. ECU. This is our high voltage product portfolio in terms of motor inverter system, as a combined package, and those are majorly applicable for commercial vehicle applications into the industry. And the voltage range here is ranging from 400 volts to 800 volt DC. And this is our inverter portfolio, which is majorly series 1, series 2, and then our series 3 inverters, which we also have like Gen 3 inverters, which are based on the Infineon Audix platform, and those are compatible with functional safety, SLD, and developed as per the automotive standard SPICE level 2. These particular inverters are developed as per automotive development standards, and you can get software which is compatible either to OpenECU platform, or the software can be made compatible as per the AutoSAR standards based on the customer requirement. So let's look at the development of motors and inverters, and what are the different types of competencies that are needed during the development of a motor and inverter. So very important stage when we start looking for a motor and inverter, or when we look at particular electrification application, we need to start looking at the vehicle and not only look at the motor or inverter as an individual system. So we have to look at customer end vehicle application, their requirements in terms of packaging, in terms of the end usage, and in terms of the usage pattern. So from there we come to a final overall vehicle level packaging of the powertrain system, and in terms of system architecture, in terms of functional safety analysis, and then allocation of different feature modules and sizing of the modules, like what would be the right architecture, what would be the right motor type and inverter type, and what would be the right size of the battery. Once here we do the requirement finalization, we start developing the individual components, and in the parallel we also start developing the vehicle control software, motor control software, and basically the hardware and software development for the complete motor inverter system. Yeah, there are possibilities where we can always use off-the-shelf motor inverter depending on the application suitability, or we might need to make some modifications and tuning for the application. So we need to then further work on components and then sub-assemblies and sub-modules like cradles, and if it requires an e-axle and e-axle based application. And then we need to go for different software level testing, and we need to go for hardware level testing, which is subsystem testing, and then vehicle level testing, and release it for the customer application. So if we go further and look at what are the different competencies and what are the skill sets that are required for developing a motor. So we require mechanical engineers to take care of your mechanical components like your case design, shaft design, bearing selection, and their applications. Then we need electromagnetic engineers who would be performing the electromagnetic analysis and work on selection of magnets, rotor sizing, and the stator sizing and packaging of the rotor and stator within the motor, and coming up with the size of the stack length and the diameter of motor and stator. Then we also need competencies in terms of CFD to majorly look at the cooling requirements, cooling jacket requirements, and designing of the cooling path. We need to go through various kinds of mechanical analysis like CA analysis, and then bearing and other NVH analysis for the motors. Then we need electromagnetic designers who work on selection of the magnets, work on the EMI, EMC part of the motor design. And then we also need to make sure that this design process is very much compliant with our manufacturing requirements, and then we need to involve our manufacturing and development team to closely work with our suppliers to make sure they are capable of developing the required components with required accuracy, or we need to go through another cycle of design to change the product requirements or the drawings. And finally, we need to have BOM technician. Now within Dana, we have managed to develop these competencies not only in one company, but one location. So gradually we are working on developing these competencies across different locations for different kinds of motors and different voltage range. For inverter design, again, similar way, we need mechanical design engineers to take care of the mechanical components, packaging, and other analysis. Then we need competencies in terms of mechanical analysis, thermal analysis. We need electrical designers for PCBA design, embedded hardware design. Thermal analysis needs to be done to properly dissipate the heat. Then we need embedded controllers, software engineers who majorly take care of complete software development and its verification validation. And similarly, we work with our manufacturing team and supplier development team to further optimize design and make it ready for production. Sorry for the bad voice. Having some struggle with cough and cold today. Yeah, so now what we see here are the different legs which are used for the motor and inverter system. So we have electrical leg, then we have performance leg, we have environmental leg, we have PCB endurance test, and we have mechanical test. So under electric, we perform the high pot test, then IR test, then back EMF test, EMI, EMC testing. Under performance, we perform the efficiency covering the different complete operating envelope of the motor, then peak and continuous power test. Under environmental, we perform the IP testing, vibration testing, shock and temperature testing cycles. And under PCB, we really test the PCB as an individual component for thermal cycling, then it's input-output testing, complete overload testing, shock and vibration testing. And under mechanical test, those are more like drop tests, dimensional checks, then connector assembly checks and tightening tests. Areas where we, as an country and as a collaborative effort between industry and academia and industry and the regulatory bodies needs to look at is specifically for electrical testing, the facility for vehicle level testing and full functional testing to meet the regulated standards. This is where we were facing a lot of difficulties when we go for EMI, EMC testing, and this did consume a lot of our time to bring our products to get the certification and bring it to the series production or bring it to the customer application. So we need to combinedly look at this to make sure that either we say the components are individually tested by the supplier and vehicle level certification is something which is taken care by the OEM, or we need to make the facilities ready so that we can do the complete component level testing at a vehicle level application, then run it through complete drive cycle. On the similar way, when we go for the performance testing, what we observed is like the AIS 041 standards currently are majorly designed for ICE applications, but for when we go for e-motor application, we need to make sure that we see the end application of the electric motor and accordingly enable the operation points and then the selection curves. And then the manufacturer should have the flexibility to define the operating points for for the continuous power tests. This is typically because when you go for S1, S2 testing, the manufacturer should be able to specify where to do the continuous power testing. Also the dyno chambers, where we need to do extreme weather testing like 85 degrees Celsius, or in worst cases minus 40 degrees Celsius. Then we need to have capability here to bring those particular temperatures within the dyno chamber. When we go for environmental testing, the chamber temperature and humidity data, we should have capabilities to properly log the data and observe the test capacities, or the how the device is being tested and what was happening during the test, so that we can properly do the debugging or use that test data for our further analysis. In terms of PCBA testing, of course, there is a need for having different benches and then the jig design, harness design, so that we can accelerate the testing time and then not lose a lot of waiting time into these areas in clarifying the requirements. Or in terms of mechanical testing, again here we do a lot of testing in house, but when we go for the certification, that if we standardize like these are the things that needs to be mentioned in the report, then it makes easy for the regulatory bodies, for our OEM customers, and for us also to finalize the report and then close the things faster. So what we see in terms of challenges, and in terms of challenges majorly faced from testing and validation are requirements that there is a need for skilled and experienced staff at different levels, because this becomes one of the problems. Of course, we also face as an organization which goes through the development, but when we bring our products to testing, verification, validation, then if there is a proper support, then we can move the things faster. Of course, when we go for the adoption of electrification, then the number of vehicles which are running in the field are limited. So of course, there is a limitation in terms of real world data. So if we do a lot of testing and acquire the data in all terms of parameters, and if we properly instrument the device, the DUT, then we will be able to get a lot of data which can be used for later analysis and learn from the testing data and draw the inferences for future development. Of course, there are test facilities available upcoming, but the current facilities are not sufficient to cover all the scenarios and all the test requirements. That's why we are very much dependent on the outside countries, and this leads to a lot of lead time in transferring the devices across regions to complete the testing, and this is becoming also one of the bottleneck. Then what we are looking at is the kind of fixtures which are designed for electric vehicle application, and basically the testing of the electric components, electrification components. There are different kinds of fixture designs that are needed, and also the standardization of infrastructure requirements in terms of the connectors which are used during the charging of your motor inverters, battery packs basically, which are used for testing. That needs to be also standardized to accelerate the testing facilities, the development of testing facilities. What we would like to propose here as an possible way ahead is if we form a consortium between the regulatory bodies, OEMs, and suppliers to standardize like what can be the testing methods, what can be the report, and what should be the content in the report, which is commonly accepted by all the parties. So we don't need to frequently run between the regulatory bodies, that the certification agencies, then the OEM, and then keep on changing. So if the reports are standardized, then it is known to everyone what needs to be entered into that, and then we go through that cycle only once. Then we should also make sure that our tests are designed considering the real world application, because most of the times motors are designed to perform at their best efficiency considering the real world usage and end vehicle application. So we should give the flexibility to the OEMs or the tier one which is bringing parts for testing to define at what parameters and at what operating points the motor should be certified, or the motor inverter as a system should be certified. Of course, to overcome the scarcity of talent in the market, there is need for a very stronger collaboration between industry and academia, which can then further offer the trainings as a part of curriculum to meet the training needs for the current market, and then also upskilling the training needs from the existing workforce of the industry. Then, of course, what we are expecting is that there should be a single-handed ownership by the test agencies or the testing parties which are performing the end testing, that we say this is a device, this needs to be tested as per the standard or as per this test, and then they take this as a complete work package and basically conduct the tests, do all the required data logging, perform the final reports as per the agreed standards, and then this will help us to minimize the number of to's and fro's and accelerate the overall development time for the product and the components. So that's all what I have to cover. Finally, I would say we all together can find a better way, and that's why we say people finding a better way to accelerate the electrification adoption in the industry. Thank you.
Thank you, Mr. Pratesh.
Yep, over to you.
Our next speaker, the third speaker of the day, is Mr. Yatish Muthappa from Mahindra Electric Mobility Limited. He has completed his graduation in electrical and electronics. Currently, he is heading the electric motor design team at Mahindra Electric. He has 15 plus years of experience in rotating electrical machines and electrical design. I would now request Mr. Yatish to share his presentation.
I hope my screen is visible.
Yes, it's visible.
Yeah. Good morning, ladies and gentlemen. Thank you, Mr. Jasti, for the introduction, and thank you, ICAT, for the opportunity given to present in this forum. So the topic is design challenges and suitability of induction motors for electric vehicles. So the contents of this presentation would be a very brief introduction of the induction motors, the power and torque of induction motors, the main requirements of EV propulsion motors, evolution of induction motors based on the weight power ratios, the suitability of induction motors for propulsion of electric vehicles, and the conclusion part. So most of you might be aware of the induction motor. This is a commonly used electric motor which works on the principle of electromagnetic induction. So in an induction motor, the electric current in the rotor, which is required to produce the torque, is obtained through the electromagnetic induction from the rotating magnetic field of the stator winding. So the rotor of an induction motor can be a squirrel cage or a wound type rotor. However, we'll restrict our discussion here to the three-phase squirrel cage rotors, as it finds its application in the electric vehicles. Induction motors are also referred as synchronous motors because they operate at a speed lesser than their synchronous speed because of the term slip, which is present in the induction motor. So three-phase squirrel cage induction motor consists of two main parts: a stator rotor, a stationary three-phase winding is placed there. In the rotor, we have the short-circuited rotor winding, which is connected to the mechanical load through a shaft called the rotor. So you can see some pictures of the motors that are being currently used in one of our programs. So as I told you, it needs a rotating magnetic field in the stator. So the rotating magnetic field are nothing but three alternate currents with the same amplitude displaced in time by 120 degrees, circulating through three windings, which is fixed in the space, whose magnetic axes are also displaced in space 120 degree electrical from each other, produce a rotating magnetic field of constant intensity. So you could see the representation here. You have 3 sets of windings of 3 phases, and you have 3 the waveforms or individual waveforms, which are like 120 degrees displaced with each other, finally producing a RMF, rotating magnetic field, which interacts with the rotor, the short-circuited rotor, inducing currents in the rotor, finally producing the required torque. So this is a simple power flow diagram of an induction motor. You could see, as I told you, the 2 parts, stator and rotor, and which is separated by an air gap. So the input power is nothing but the P1, which will be feeding the motor, and the electromagnetic power in the machine air gap is nothing but the input power minus the losses that are accounted in the stator. The losses are the iron losses, that is the core losses, the I squared losses, and the stray load losses. So the electromagnetic torque in the machine air gap will be P by omega. So that is what I've shown here, and the effective power on the machine shaft is nothing but the electromagnetic torque in the machine air gap minus all the losses that takes place in a rotor. In an induction motor, it is like the rotor iron losses, the rotor I squared losses, which is present here because of the presence of the rotor bars in this kind of machines. You have the stray load losses and the mechanical losses, which are inclusive of the bearing losses, the ventilation losses, and the friction and windage losses. So the effective power on the machine shaft is nothing but the input power P1 minus all the losses, and the effective torque on the shaft is the power in the shaft upon omega. So this slide shows us the importance of efficiency here, because the higher the losses, we have lesser power on the machine shaft, and subsequently the lesser torque which is available on the shaft. So the main requirements of the EV propulsion motor is to have high efficiency in different drive cycles, high starting torque, wide operating speed when we talk about the electric vehicles, high power density, better power factor, smaller size, it has to be compact, low cost. Typically, the torque speed curve and the power speed characteristic of electric motors is designed in this way. We could see that a higher torque at the lower speed till you achieve the base speed, and it is expected that we have a constant power region, or a wide constant power region after the base speed. This picture represents the evolution of 3-phase induction motors. I mean, induction motors are not new in the market. They are in the market for more than 100 years, and there has been a lot of developments over the years, mainly on the materials, mainly on the optimization techniques. So you could see a gradual reduction in the weight power ratios, and when in the initial days it was like you could see that a 1 kilowatt motor would weigh around 88 kilos, and now we are in a stage where we are able to design a kilowatt motor with a 2 kg or lesser than, slightly lesser than that. So this is very important, because this reduction in the weight power ratio has resulted in induction motors being considered for the electric vehicles, where the cost and the size is of utmost importance. So along with the optimized winding design, there are the characteristics of induction motors largely depends on various geometrical structures, which include the stator rotor slot geometries, the diameters of the stator and rotor, the coaxial length, the slot profiles, the combination of slots, the dimension of the slots. So the slot profiles and dimensions can be varied to obtain the optimal performance of an induction motor for an EV application. So you can see one profile that we are using for one of our programs, where for a 3-wheeler where we are trying to use an induction motor because of some of the advantages that it offers. Here is a small comparison just to show the effect of some of the effect of the slot profiles and the geometry that we were talking about on the motor characteristics. So when I talk about motor characteristics, it is mostly on the torque, the power, and efficiency, which is like which is most important when we talk about motors for the electric vehicles. So you could see a scenario where we have a stator slot profile. So you could have n number of profiles, but I've considered 3 profiles where the simulations are done with the different slot profiles, and just to see the impact of torque and the power and efficiency. So you could see that there is no much difference. I mean, the contribution of stator slot profiles, I mean, there is no much impact on the characteristics. You could see the torque levels on the similar lines, and efficiency, there are slight differences. When you come to the rotor slot profiles, you could see 3 options where it has a very good impact on the characteristics of the motor, because the resistance and the reactance of the motor has a direct dependence on the torque. So you could see option 1 with 43.3 Newton meter torque, and gradually increasing, where option 3 can deliver us 51.81 Newton meter torque with a higher power and also better power factor and efficiency. A scenario where we can see the impact of the diameters and the diameters of stator and rotor laminations on the characteristics of motor. We have 3 diameters, 125, 150, 175, and you could see that higher the diameter, the impact on the motor characteristic is very high on the torque, power, and efficiency. So it implies that higher the size of the induction motor, definitely you'll be having a better torque, power, and efficiency. And on the coaxial length, the core length, we have 3 options here, where you could see that on the similar lines that a higher length machine will have a better torque compared to a low length machine, and also better efficiency and power factor. So a typical torque speed, power speed characteristics of induction motors for EV. This is also from one of the motors that we are using in our current line. As I discussed, peak torque, I mean the maximum torque till the base speed here, and the torque gradually reduces with the increase in the speed. The power, you could see that in induction motors, it's very tough to achieve a constant power throughout a wide speed range. So you could see like from close to 2000 to 4000, you're able to achieve a constant power, and it gradually goes down. This is mainly because of your lower efficiency that we have in induction motors, gradually lower efficiencies when we compare to PMSM or some other kinds of motors. So for sure, there are disadvantages of using induction motors when we compare with the permanent magnet synchronous motors for EV. We have lesser efficiencies, lesser torque densities, reduced constant power operating range, what we saw in the previous slide, higher weight, bigger volume, high current and constant torque operation to overcome the lag in the efficiencies, the thermal limitations due to relatively low efficiency. However, the induction motor also provides some advantages compared to the permanent magnet synchronous motors. It is very simple and rugged in construction, which making it suitable to be operated in the harsh environmental conditions. It literally needs no maintenance, very low maintenance. It's cheaper due to the absence of high-cost rare earth magnets when we compare it with the permanent magnet synchronous motor. The absence of rotor position sensors, unlike in PMSM, it's important to have position sensors in PMSM. Low production cost due to ease of manufacturing, because we have these induction motors in the market for more than 100 years. So all the processes, all the methods are already established, and the big advantage what we see here is the better management of supply chain due to absence of special materials. So when we talk about EV, we're talking about mass production. So since there are no special materials involved here in the induction motor, so it offers an advantage of better management of supply chain. There are methods to improve the efficiency of induction motors, the conventional ways where we use a low loss silicon steel laminations to reduce the constant losses. Some of the manufacturers are going with very thinner laminations, 0.25 mm laminations to bring down the eddy current losses and also get that benefit on the constant loss. Optimization of slot fill factors to reduce the variable losses, which is nothing but the I-squared losses. Higher core lengths and diameters offers us an option where we can go for an improved efficiency. Design optimization with adequate slot configurations and profiles, the same what we saw in one of the comparisons. optimization of bearings in order to reduce the mechanical losses, optimization of thermal circuits in order to reduce the ventilation losses. So with this, I would like to conclude with reduction in the weight to power ratios of induction motors over the period, and due to its reliability, ruggedness, low cost, and suitability for wide-speed operation, the induction motors are one of the best suited solution for propulsion of electric vehicles. It offers a disadvantage. The main disadvantage of relatively low efficiency can be overcome to some extent by adequate selection of lamination materials or geometrics and geometrical considerations. So continuous efforts in improvising the induction motor designs for EV are of very much importance, so that we reduce the dependency on the rare earth magnets when we compare it with the PMSM, making it very simple and easy to manufacture. Thank you. That's it.
Thank you, Mr. Yatish Muthappa, for enlightening us with way forward in e-drive system with induction motors. These motors are the best when it comes to the efficiency. This is indeed an interesting topic. We'll have question and answer session after the fourth speaker today. Our last speaker of today is Mr. Kundan Yadav from Euler Motors. He is graduated in electrical and electronics and currently working as a core member of the electrical controls in motor design. I would now request Mr. Kundan to share his presentation.
Hi, Jastik. I think you can see my screen, right? Hello.
So yes, we all can see it.
Yeah. Okay. So first of all, thank you for having me here. I would like to thanks to ICAT to give me the opportunity to talk about the efficiency of the motors and how we are optimizing the efficiency of the motor. So as like we started in 2018, Euler Motors, we started in 2018. So you know, I want to add my first-hand experience by directly interacting with clients and customers, and I want to paint a different picture. All the speakers seems to be ancillary in how we are planning testing and challenges. Each customer are different. So in best case scenario would be to have a personalized driving experience over the powertrain. So like first of all, I will talk about the efficiency optimization parameter in terms of design. So how you are selecting the geometry, means number of phase, number of poles, slots per pole, so all the like all the main dimensions that are dependent on ABC factors, that is called current density, flux density, and the cooling. So if you are using natural cooling, then your current density will be around some 4 ampere per mm square area. So if you are optimizing your cooling system, like if you are using cooling jacket, then you can increase the current density from 4 to 20. So these are the most important parameters to select your OD, ID, stack length, etc. Apart from that, when you talk about the rotor profile optimization, that like whether you are going to how will your magnet shape, it will be V shape or other shape depending upon the harmonics available, harmonic distortion available. So according to that, you have to shape your rotor skewing. Your rotor should be skewing, or you don't need a skewing. So these parameters also depend upon the slots per pole. If it is integer, then you have to make it skewing, and if it is in fractional, you don't need to skew. So these are the parameters. So like I will also talk about the data we have gathered from the field. There are a lot of sensors that we have implemented in our vehicle. So we are gathering data in during downhill, during uphill, and in flat road. So we have plotted some efficiency, heat distribution map where our vehicle is operating most of the time. And so using some different sensors. So where we have to optimize the method. So first we have to understand in which region we have to optimize our motors. So we have gathered a lot of data from the fleet, depending upon how driver is driving the vehicle, and different drivers having different mindset to drive. Someone is driving very fast, someone is driving in average speed. So we have gathered these data, and according to that we are optimizing our torque and RPM. If torque and where we have to optimize our motor in which RPM range, in which torque range. So according to that, I can show you this efficiency contour plot, which shows your motor is more efficient. This is for induction motor. Basically, I have plotted this contour plot. So you can see here the peak efficiency of the motor is 84%, and average efficiency, if you consider, that is 70% in induction motor. When you and also the other speakers mentioned about the induction motors, that weight is also higher and the efficiency is lower. So that's why right now the industry is shifting towards the IPM and switch reluctance motor. Because of the efficiency challenge, because if you increase the efficiency by 1%, you can increase by 4%. So we have gathered these data from the fleet, and so that's why we are shifting to IPM motor. So that's why I have written here how to first optimize the parameters, like a stator profile optimization, slots shapes, teeth shapes, yoke thickness. So these are the main parameters that directly affect the efficiency of the motor. And the second thing is winding. So number of turns per phase. Suppose if you want to increase the base speed of the motor, you have to decrease the inductance. So inductance is directly proportional to your number of turns. That is, L is directly proportional to N square. So if you want to increase the base speed, then you have to do the field weakening. So these are the parameters that we have considered while designing our motors. Slot, fill factor, layer, what should be the layer. So most of the companies I think using double layers for winding, and the pattern, whether it is lap winding or concentric winding. So these are the main parameters while designing. We have to consider while designing the motor. Also the materials that you are selecting for magnets. So that's for windings and lamination, which materials you are selecting. And if you are selecting those materials in best way, then your cost should also not go that much higher. So that you have to consider those parameters also in your design consideration. So I already talked about these parameters, so how we are optimizing our motors and all. So motor tuning, my next topic is motor tuning. So tuning for motor, first of all, we have to find the inductance of the rotor and rotor resistance using short circuit test and open circuit test. So first of all, for a speed controller PI loop, we are tuning KP by KI, which is equal to J by B, where J is inertia constant and viscous coefficient. So how you are doing in that setup, we have multiple we have regenerative dyno, motor dyno in house, we have chassis dyno in house. So first of all, after designing the motors, after all the simulation in Maxwell software or MotorCAD, so we used to analyze those data over the motor dyno. So how actually in critical there is you have not considered you will not think in motor when you are testing in motor dyno. So what will be the output of your simulation? So those data we are tuning in the motor dyno, then we are shifting to chassis dyno in vehicle level, and then we are doing the ground test. And the advantage of working in a startup, you can directly communicate, directly interact with customers. Every customer is having different experience or different different demand, how, and also there some like some speakers talk about like by we shifting from IC engine to electric vehicle. So the regenerative is meant is also a factor that we shifted from IC engine to electric vehicle. Yeah. So this is the efficiency plot that I discussed. So in terms of IPM motors, efficiency increases. The peak efficiency we saw around 96%, and the average efficiency of IPM motor or PMSM motor is around 90%. So like if you like I already talked about, like if you're increasing efficiency by 1% of the motor, then your range will increase by 4%. So you can consider like the average efficiency of the induction motor compared to IPM motors. So yeah, that's all from my side today. Thanks, team.
Thank you, Mr. Kondan. Thank you for your presentation. Well, now I would like to borrow some time to show you the ICAT testing capabilities. Let me share my screen to all of you. Yes, I hope I'm audible to all of you. So ICAT was established in 2006, and ICAT is providing services in the field of automotive and testing, validation, design, and homologation. We have a manpower strength of 492, and also it is located in Manesar, Haryana. We have 2 centers over here. So ICAT was established under an entity named as NATRIP, which was formed under the MHI. The whole investment done by NATRIP was 3,742 crores, in which ICAT shares an amount of 1,350 crores. For ICAT, we have here provides we are authorized to do testing for type approval and COP under CMVR Rule 126, and also for CPCB and noise type approval testing. We are accredited by the NABL, VCA, and BIS standards. All the facilities in ICAT are being certified by IMS and the NABL ISO 17025. We are partners with certification agencies from Korea, with ADIADA from South Africa, TUV, NOR, TUV SUD, and there are several MOUs being signed with the agencies from Korea, China, Millbrook, UK, Brunel University. So let me just start with the electric motor test lab capabilities, which the ICAT offers the services. So basically in 3 domains we are offering the services: the certification, the performance, and the durability of electric vehicles on a e-motor test bench level. So in a motor and inverter level validation, there are four categories in which testing are being done. First one is electrical and mechanical power testing. The second is performance testing in traction, acceleration, or regeneration mode. Third is road load cycle simulation on motor with dyno. And the fourth is the durability testing in the low and high ambient conditions. These are the some of the tests which comes under the DVP plans of the customers, of the OEMs, which we have already done for OEMs like Tata and Mahindra. So under electrical and mechanical power testing, our labs are capable to do the power factor, phase angle measurements, the DC inverter, AC inverter output measurement, the RMS and average data, inverter, mode switching, efficiency, and tuning. All these things can be done on one single test bed in automation, and the data can be further analyzed to optimize the efficiency. Under the performance testing, these are the tests which are there: the peak torque and peak power measurement, the total loss and total efficiency, temperature rise, torque characteristics, torque ripple, cogging torque. All of these tests are already also covered in the IS standards. Then the road load cycle and durability testing. See, the lab is the testing which we do in a controlled environment, but yes, we can have the data from field data from automotive an EV electric vehicle, and that data captured in the field data that can be simulated in the test bed, in which we can do further additions. We can do thermal shock testing with the coolant temperature of, let's say, from 10 degrees to 110 degrees Celsius. The transient cycles with predefined torque RPM points, performance at lower and higher voltages, overspeed test, thermal mapping, impedance, waveform, and power factor measurement. These are some standard tests which we conduct under the regulations, the net power test and 30 minutes power test under the AS41 and AS137 Part 5. Performance testing of the motor inverter under ISO 21782. Motor power test under European regulation ECE R85. And also we do the non-standard test based on the customer's requirement to validate the product in India. These are the test bed capabilities which we have over here. The lab capability is to do testing of an e-motor ranging from 1 kilowatt to 380 kilowatts. We have dynamometers of multiple ranges, 430, 165 and 25 kilowatts, with the torque and speed characteristics given over here. The testing can also be done without any interruption as we have battery emulator units installed, so constant DC power supplies can be given. Along with that, cooling system are there to control the temperature and also the flow of the motor in case they are water cooled. These are some case study projects which we have done in a collaboration with OEMs in India. These are some setup pictures in which we have done the overspeed trials, the efficiency mapping, the field data simulation. So we took the data from the vehicle on a rural and urban area, and we take that data and we load it into our system, and we ran the endurance and the efficiency trials. Also, some trials with high ambient conditions were done. As you can see, an enclosed chamber is there, which is covered, which has the motor and inverter system. So we can do a dynamic testing in a high ambient condition up to 90 degrees Celsius. Also, the lab's capability is to not only do the automotive electric motors, the AC industrial motor testing is also being done for vibration data measurement and for sound level checks. These are another example of case studies in which we did a trial basically to know the belt and chain efficiencies with an electric motor. The hub motor testing also being done with a smaller dynamometer over here. The instrumentation shown over here, we have the instrumentation from Hyoki, Yokogawa, SPM. Thank you. That's it from the presentation. I would now like to request Mr. Sitaram Kashyap, DGM E-Motor Lab, to deliver the vote of thanks.
Thank you, Jasdeep. I take this opportunity to thank prominent guests and speakers to have grace on this successful webinar. Thank you, respected Pamela ma'am, Official Director ICAT, for her vision and guidance, which has led us to being the prominent certification agency and to have added another feather by offering development and certification services in field of e-motor testing and powertrain. Also to be mentioned, Mr. Prabhu Santiago, speaker from AVL Graz, for showing the new way ahead through the insightful presentation, model-based technology using Cameo 5 to provide optimize NVH and efficiency of e-motors. Mr. Prabhu, thank you very much for your time and travel for early rising and giving this time for this webinar. Our next speaker, Mr. Pritesh Doshi from SS Dana, for showing the collaborative thoughts on testing, validation, and designing of e-drive for light vehicles, off-highway vehicles, and commercial vehicles. A special thanks to Sri Kundan Yadav from SS Euler Motors to shedding light on efficiency mapping and optimization using ABC factors. Optimization of induction motors being a hot topic in the current scenario, being the best research for efficiency optimization, thanks to Sri Yatish Muthappa from SS Mahindra Electric for sharing his wisdom with us on torque, speed optimization, power torque optimization, and optimizing the best performance on electric motor and reduction of weight and power ratio. Lastly, our participants who are connected with us today, thank you very much for your availability and gracing this occasion by using this webinar and being a part of this, making it successful by your esteemed presence. We are delightful to see such a huge response, and having received more than 400 participants from the industry, we look forward for continuing these initiatives. The content of the speakers align with today's industry requirement related to electric motor testing. ICAT is always there to support industry and end user to meet the expectations in terms of facility and capability for the certification and validation of e-motors and electric powertrains. We have wide range of dynamometers starting from 25 kilowatt to 800 kilowatt, and we can test e-motor up from 1 kilowatt to 400 kilowatt. I want to thank my colleague Jasdeep, who has wonderfully made this efforts to have this successful webinar by inviting all you, and there is a huge participation and make good efforts to make it successful. And thanks to my team ICC, Mr. Bighu and Krishna Govind, who has contributed a lot for providing this infrastructure and connecting all you. Thank you all once again, and see you soon in physical seminar in very near coming time in ICAT. Jai Hind. Thank you very much. Namaskar.
Well, thank you, sir, for your motivating words. We will now have the question and answer session. The first question is for Mr. Kundan Yadav. So the first, what is the effect of radial flux and axial flux on the efficiency or other parameters? Hello, Mr. Kundan, can you hear me?
Yes, I can hear. Yeah, can you repeat?
Yes, the question is what is the effect of radial and axial flux on the efficiency of the motor or any other parameter?
So right now, most of the ITM motors are radial flux motor. Axial, like when you because in automotive industry, like we need higher torque at low RPM. So axial flux, axial flux motor, which is like used in higher RPM, but that time we cannot achieve the higher torque. So efficiency, like it depends upon the application also. So if you want to achieve the efficiency in lower torque and higher RPM, then your axial flux is better. And when you talk about the higher torque, because in automotive like commercial vehicle, so we are seeing the average speed of the vehicle is around 25 to 3,500 RPM. So according to our heat map analysis that we have done from the roadmap, we have from our 1,000 vehicles that we have deployed in the field. So according to that, we saw like most of the operating region are around from 1,000 RPM to 3,500 RPM, and torque range is from 0 to 25 to 30 Newton meter. So in that range, the radial flux motor is more efficient. So that's why you can also see in industry most of the company are using only radial flux motor.
Okay. Thank you, Mr. Kundan, for your answer. The next question is to Mr. Prabhu Santiago. Hello, Mr. Prabhu, are you there?
Yes, I can hear you.
Yes, the question is, as you have mentioned, the while doing the efficiency mapping of a motor, the NVH also comes into a role. So apart from the NVH, considering the NVH, apart from the motor's design, the rotor and the stator, the balancing, what all other parameters which comes into the role, like the surroundings of the motor's mounting in the vehicle. So what all other NVH parameters comes into the role? This is the question.
Okay, here at least my presentation, what I focused on was the calibration of the MCU parameters to have the best trade-off between efficiency and NVH. Of course, there we are just measuring the structural NVH of the motor. Of course, when the design parameters and also the mounting parameters affect NVH quite significantly. Okay, this is a separate discussion, but my focus was that even the MCU parameters affect the NVH of the motor, and we have to calibrate these parameters to have the best optimization. So yes.
Hello. Yes, thank you, Mr.
Yes.
Prabhu. Yes, the next question is for Mr. Yatish Muthappa from Mahindra. So this is an interesting question. Why do we need to convert AC to DC or DC to AC? Why can't we use DC motors which can provide same output as AC? Hello, Mr. Yatish, did you hear me? Should I repeat the question?
Yeah. Can you repeat the question, please?
So the question is, the person is asking that why do we need to convert AC to DC or DC to AC? Why can't we simply use the DC motors with a similar output like AC motors?
It's an interesting question. AC motors, I mean, DC motors have their disadvantages, right? The main problem with the DC motors is the commutation and the brushers, and the maintenance of DC motors are difficult. So AC motors are much more easier to maintain, and as I showed in a presentation, that it's literally maintenance free. So this is one of the advantages what we get in AC motors.
Okay, thank you. So the another question is for ICAT. So what will be the range of closed chamber? Yes, so that the ambient conditions around the motor inverter, that closed chamber which I showed, so that can be a temperature of 90 degrees can be reached, and testing can be done. However, with some more modifications, it can further be increased. So would like to have your detailed scope requirement. You can forward it on the mail ID mentioned on the flyer. Thank you. Let me just go through the other questions. So yes, the next question is from Mr. Yatish. The person is saying that even though we see the market is shifting PMSM and SRM, apart from cost and supply chain parameter, will Mahindra Electric adopting PMSM or SRM for its compactness and higher efficiency? I think, yeah.
Yeah, we have some programs with the PMSMs. I'm not denying that, but it depends on the vehicle requirement and the actual operating characteristics required from the vehicle, the range required. So if you take a small vehicle or a three-wheeler, we have found in some of the programs where induction motors were giving us good benefit. I mean, meeting along with meeting the requirements of the vehicle and also the supply chain and the cost part of it.
Okay, thank you. Yes, the next question is for Mr. Pritesh Doshi. So it's for Dana product, related to Dana product only. So why Dana use high and low voltage motors with a very low RPM?
That's an interesting question. So typically, when we go for the kind of application that defines the motor RPM. So currently, the motor portfolio that I have shown in my presentation for high voltage application is a direct drive type of application, and that's where you see that the RPM requirement is only the final drive reduction. But we do have high RPM motors which are going for our passenger car applications also. So it's not that we are restricting ourselves to only one particular RPM range. So as I mentioned and shown into my presentation, like there are different technologies that we use while designing and defining our motor type, and we do have motors which work in higher range also, depending on the application need.
Okay, thank you, Mr. Pritesh.
Yep.
Well, there are a lot of questions asked to ICAT team. So I would like to mention and tell them to please float your inquiries to the ICAT special mail ID so that we can answer your take your case further. I think that's it from the question and answer session. We'll now conclude this session, today's day. On behalf of ICAT, I would like to thank everyone. We are thankful to all these speakers who spared out time from their schedule, and also the participants from the industry for such a wonderful participation. We look forward to continue this webinar series on challenges and opportunities of an electric motor. Thank you very much.
Thank you.
Thank you very much once again.
Thank you.
Yeah, thank you.
Thank you.
Thank you all. Bye.
Thank you.
Thank you.